First of all, I'd like to thank you for inviting me to this workshop. And I will present our recent progress in peridynamic theory within the next 40 minutes. So here's my outline. I'll give you a basic sort of introduction to peridynamics, peridynamic equation of motion, and certain anomalies in peridynamic theory, and then show you some applications, and then end it with some remarks. So peridynamic theory is a non-local approach. Basically, if you have a point X here, it's going to be interacting with other material points within its finite distance. So this distance is referred to as the internal length parameter, which serves as, we refer to it as the horizon. Okay, the internal length parameter is missing in the local theory. Also in peridynamics, we do not have any spatial derivatives. So that means we don't have any smoothness requirements. Okay? So damage initiation and propagation is very simple. All you have to do is you basically remove the interactions between these 2 points, and you initiate damage in unspecified locations, and damage propagation occurs paths. As you can see here, this is the simulation of this particular cracking that's taking place in this chemically treated glass. Okay, so you can have emergence of multiple damage sites and their complex interactions. So it's very robust when it comes to predicting failure. And that's the main reason why it was introduced by Stuart Silling in year 2000. So it's very simple. This is the equilibrium equation that we're all familiar with. P is the Piola-Kirchhoff stress tensor. So what Silling did, he replaced the divergence of the stress tensor with this integral representation here. And the integrand doesn't have any derivatives. So it's valid regardless of discontinuities, such as cracks. And the domain of integration here serves as the domain of interaction. Okay, so the domain of interaction, for example, for point X, is this circle here, X. As the radius of the circle approaches 0, this integrand actually recovers the divergence of the stress tensor, as proven by Silling and Lehoux in 2008. Okay. And the force density vectors that occur as a result of this deformation taking place is acting on X and X prime. Okay. And the force density functions contain all of the constitutive information associated with the material. So that the constitutive relation come in through the force density vectors. Okay, so these equations were derived by Silling for a material point symmetrically located in the domain of interaction. Okay, so if the material point is not symmetrically located, then you're going to have basically an unsymmetric position, and that's going to create some concerns that I'll talk about later. Okay. Also, what doesn't come out of the derivation of these equations, the boundary conditions, do not emerge as part of the derivation. But in real life, we need to impose boundary conditions, so which is not consistent with the classical continuum mechanics. So we can classify peridynamics into bond-based, state-based, and the bond-based, I'm not going to go into the detail. In the case of bond-based, you have force density vectors acting at X and X prime. They're equal and opposite in magnitude. And in ordinary state-based, T and T prime could have different magnitudes, but in opposite directions. In non-ordinary state-based peridynamics, you have force density vector at point X and X prime going in different directions. What is attractive about this non-ordinary state peridynamics is that we can use directly the classical constitutive models that are already available in the literature. So then if I look at non-ordinary state-based peridynamics, and if I'm going to use the classical constitutive models, that means I have to have a peridynamic representation of the deformation gradient tensor. And this is what's introduced in 2007. So that's the peridynamic representation of the deformation gradient tensor. Here what you see is the omega is a weight function, okay, which controls the degree of interactions. And y and y prime are the position vectors in the deformed state. So x becomes y, x prime becomes y prime. And xi is the relative position between x and x prime, and the shape tensor, which is basically a tensor that gives us the relative position of x with respect to x prime in its family. So we equate the strain energy density coming from peridynamics and classical mechanics then we can come up with an expression for the force density vector in terms of basically this Piola-Kirchhoff stress tensor, and this vector G is expressed in terms of the weight function, the inverse of the shape tensor, relative position vector. So this Piola-Kirchhoff stress tensor is going to come in by taking the derivative of the strain energy density function, because we know the peridynamic representation of the deformation gradient tensor. And we put to the equations that I showed you here, T and T prime, then we can basically construct this equation, which is nothing but the F equals MA. Okay, so here you have P, G, P prime, G prime. What is the issue with this equation? So basically what you have is you have zero energy deformation modes. As you can see here, you have a bunch of oscillations here. That's the result of that, right? Zero energy deformation modes. Also, what you have is when you directly impose the boundary conditions, you're going to end up with stresses. Okay, so these are basically you're going to have some stress concentrations because of the kinks that you have near the boundaries when you directly impose the boundary conditions. So as I mentioned before, really the major sort of strength and robustness of peridynamic theory is that you can introduce damage very easily by breaking the bonds, right? So when a bond, the stretch of that bond or the interaction reaches a critical value, then you break the bond, you introduce a status parameter. If it's intact, it's 1, if not, it's 0. And that's the stretch you define for small deformation, that's the stretch you define for large deformation. And through the status parameter here, if the bond is broken, so the contribution coming from this particular interaction is gone. So that's the way you break the bond, but breaking only one bond doesn't mean that you're going to have a cracked surface. So what you do is you look at the ratio of the broken bonds to the total number of bonds that you have at a particular point, and we refer to this as the local damage. The local damage becomes, let's say, 0.5, then we say, okay, you basically introduced a cracked surface. Okay, so that's very simple. Now, as part of this talk, I'm going to basically talk and as we will compare software and some issues of that.
I think there is something wrong with his internet, but probably he will join us soon.
So basically, I'm going to go over the recent progress that we made in peridynamics. One is removal of spurious oscillations. The other is direct imposition of local boundary conditions, both in weak form and strong form. And then I'm going to show you that as a result of this, we're able to couple a finite element method with peridynamics in a commercial software. And let me go to the presentation mode here. Okay. So if we go back and analyze what's happening in ordinary state-based formulation. So let's say you have a point X, symmetrically located, X prime is also symmetrically located. And let's assume that you have homogeneous deformation, okay, Y F not X. If we put this representation in the peridynamic representation of the deformation gradient tensor given by Silling, 2007, this is what we end up with. So the peridynamic representation is exactly the same as what we specify because homogeneous deformation F naught. So I'm going to use the strain energy density associated with it, take the derivative, end up with Piola-Kirchhoff stress tensor is P naught. Put it back into the equilibrium equation, and this is the final result we end up with. P naught is uniform, and K naught is because X is symmetrically located, X prime is symmetrically located. The shape tensor is the same at these 2 points. I'm going to call that K naught. So I pull it out. So I end up with this integral here. Because of the real symmetry we have at this particular point, it's 0. So the equilibrium equation is satisfied, right? As long as you have a point in a full horizon at both point x and x prime, then the equilibrium is satisfied. But what happens if you go to a point where you have x and x prime are not symmetrically located? The shape tensor is not going to be equal to each other, right? X and x prime, they're going to be different. I have the same homogeneous deformation. My Peridynamic representation of the deformation gradient tensor is the same. Pure-Kirchhoff's stress tensor is the same. Sure enough, what happens is if I put everything into the equilibrium equation, it's not satisfied.
Madenci, can you hear me? I think there's a problem with your connection, so it is not stable. Dr. Madenci, we cannot hear you. Can you put it on mute mode?
Okay, can you hear me now?
I can hear you, Dr. Madenci. If you want, you can stop sharing your camera. Maybe your connection will be better.
Okay, let me try that.
You can only share your screen. Yeah, I think that will be better.
Do you see my screen now?
No, not yet. Maybe you can try it one more time.
I think the internet is extremely slow. Can you see now?
It's coming. Okay, we can see it, Dr. Madenci. Yeah.
Okay, so the alternative form of the peridynamic equation of motion is we can use the peridynamic differential operator to rewrite the divergence of the stress tensor here by using the peridynamic differential operator. And we can also write the peridynamic representation of the stress tensor. Okay. So the equation looks like P prime times G minus P times G. So with this representation here, the point X and X prime do not have to be symmetrically located in the interaction domain. As shown here, X and X prime have a non-symmetric position. So, and it doesn't have zero energy deformation mode, so you have free of oscillations, and you don't have unphysical stresses due to the direct imposition of boundary conditions. So with this in mind, then we also look at a homogeneous deformation, like similar to what I did before, and I evaluate the deformation, basically in this case, for this deformation, for this homogeneous deformation, I'm going to look at what's happening, the deformation gradient tensor associated with this particular interaction. I'm going to call that F psi, and that's equal to F naught, and the corresponding stress is P naught, but I'm using the orthogonality property of the peridynamic functions. So in this particular case, regardless of where the points are, X and X prime, whether it's in the interior or near the boundaries, equilibrium is always satisfied, okay? So how do we remove these spurious oscillations? We know the root cause of this problem. It's because of the radial symmetry. If the radial symmetry is not there, then these zero energy deformations are gone. So if you, as suggested by Chen and Spencer in 2017 or 18, so if you look at the intersected interaction domain here, so X has the domain of interaction HX, X prime, HX prime. So if you construct the deformation gradient tensor for this intersected region here, then you don't have any radial symmetry. So then the problem is gone. So what we do is we call that the bond-associated deformation gradient tensor. So for the bond-associated deformation gradient tensor, so this is the intersected domain, and I identify that particular deformation gradient with a particular bond. I call that psi, and that's the expression we have for that. And G psi is the peridynamic functions, right, that we construct in advance. And once you have the deformation gradient tensor, you can take the derivatives of the strain intensity function. Then you have the Pure-Kirchhoff stress tensor associated with that particular bond. Again, we go through the same procedure as before. We equate the strain energy density coming from peridynamics, classical continuum mechanics. We obtain the force density vector for that particular bond, and we write the equilibrium equation in this particular form here: P xi G, P prime xi, G prime. It's very similar to what Slinky derived in 2007, but the only difference is that we identify the deformation gradient tensor with a particular bond rather than with a point. And this concept was introduced by Chen and Spencer in 2018. We also used it later on in 2018 and 2020. So the peridynamic differential operator is very straightforward. If all you have to do is basically you can reconstruct the local derivatives in terms of its peridynamic representation, as long as you construct the peridynamic functions. So here's point X interacting with X prime, arbitrarily located. And so what you do is you can assume the peridynamic function to be, let's say, polynomial. And these are the unknown coefficients. And these are the components of the relative position vector in this case. If you basically determine these coefficients by satisfying the orthogonality property here, then you have the peridynamic functions, you put it back in here, then you perform the integration over the domain of interaction, then you get the local derivatives of any order you like. And so if you are interested in this particular operator, so there's a book out, Peridynamic Differential Operator for Numerical Analysis. And so it's also translated to Chinese last year, so it's, so how do I basically impose these boundary conditions in the strong form, right? So this particular equation that I showed you was derived by Slinky 2007. It's good as long as you have point X and X prime fully embedded in the bulk of the material, away from the boundaries, and that's region D. And if I use peridynamic differential operator, which is valid everywhere, right? But I'm going to use it in this region here. I'm going to call this region R. That's also fully satisfied, as I showed you before. And in the region, because I want to impose the boundary conditions here, the boundary layer region B, I'm going to write down the peridynamic representation of the Piola-Kirchhoff stress tensor. So basically at every point that I have, I'm going to apply these equations. I'm going to end up with the discrete form. These are the set of equations I have, and impose these boundary conditions. T star is the applied traction vector, and U star is the applied displacement. So that's the set of equations I have. So I'll show you an example of this, right? I have many examples, but because of time constraint, I thought I'll show you this. So a small deformation, plane strain conditions, and you have basically this particular plate on roller supports, and I'm going to apply a displacement constraint, and this edge is free of tractions. So now I basically discretize my domain as the boundary layer region, and this region here, I have the equilibrium equation coming from the peridynamic differential operator, and here is the equilibrium equation that's coming from the non-ordinary state-based formulation. So the horizon size is 3 delta x, and we apply this loading. I'm showing you the horizontal displacement and the vertical displacements here. It's nicely varying linearly as expected. Everything looks good. The contours look good, but let's look at the line plots, okay? So I'm going to compare what we predict against FEM, and also what we predicted in the past. I'm going to call that PD previous. You see these displacement kinks here, and they result in these unphysical stress concentrations near the boundaries. See, no longer exists, okay? And I'm looking at, in this case, horizontal displacement and the vertical displacement along the edge here, basically along this point here. And also I'm showing you the normal stresses in the plate. See, this is the present formulation, and this is the previous formulation. You see these stress concentrations here. They go from 403 to 2,800. Okay, so you clearly eliminate the unphysical stress concentrations. Now, then we move on to the weak form of peridynamics. So we start with principle of virtual work. Again, in this case, we discretize the domain into a boundary layer region, the interior part of the region. We go through the principle of virtual work and discretize our equations. And then we end up with this system of algebraic equations. And this VB here basically has the unknowns associated with the bulk material points in the bulk of the body. And VT and VU, these are the unknowns associated with the material points in the boundary layer region. So I'm going to show you a couple of examples. The first one is rupture in polymers. So we're going to use this particular strain energy density function here, the isochoric part, the dilatational part. And so that's our strain energy density function. And I'm going to use the Taylor series expansion of the longitude function here. And this is this has a slight compressibility. It's known as Anand's model. So we're going to use plane stress conditions. So for us to enforce the plane stress conditions, we have the second periodic Kirchhoff stress tensor. We enforce this, we end up with a constraint condition that we have to satisfy. C33 is the one of the coefficients of the Cauchy-Green strain tensor, right? Cauchy-Green strain tensor. So we have to basically solve for C33. And so here's an example. I have a rubber sheet with double edge cracks. And this particular specimen was considered by Hossein and his colleagues in 1998. And they considered the crack length to be 12, 16, 20, 24, 28, 5 different crack lengths. And everything else is the same. But the only thing that we don't know in this particular case is the critical stretch. So what we did is we used one of these configurations, in this case, crack length being 28 millimeters. We basically calibrated the critical stretch for this particular case. Okay, so reaction force is a function of applied displacements. And then after we calibrated this, for the others, the remaining 4, we use the same critical stretch and predict reaction force versus applied displacement. And that's what we get. So reaction force, applied displacement for 12, 16. So they're fairly close to each other with the experiments, and also another approach given by Talamini. They use finite element method coupled with phase field. And again, for 20 and 24, they're pretty consistent. So here I have a, see, as you can see here, basically the crack starts opening up and then keeps opening, and then it goes through the starch deformation, it basically ruptures. And I'm showing you here the vertical displacements as the crack propagates. And then we said, okay, well, let's look at some other examples here. So we look at this PDMS sheets, and here you have an edge crack and an internal crack. Okay, so we chose the critical stretch to be 4.1, and I'm going to skip all the details here, but I have the edge crack and the internal crack here. Then we compared the normal stress against the stretch against the experimental measurements. Okay, so this is the damage prediction here. As you can see here, it very nicely captures the experimental observation here. And here, the one with the internal crack. So then we move on to another application where we have bonded lap joints, where you have viscoelastic adhesive, you have elastic adherence, you have finite deformation. I'm not going to go through all the details here, but the same idea, we're using the weak form of the non-ordinary state-based formulation. And I'll just go ahead and show you some examples here. You have these aluminum adherents, and you have this FM73 adhesive. We only model 1/4 of it. And so we're going to apply this constant stress. We have the viscoelastic response to the material is expressed in terms of Prony series. And again, everything else is the same as what I showed before. Of course, we compared the horizontal displacement, the vertical displacements against finite element results before we turn failure on. And once we're satisfied with the displacement predictions, the accuracy of the results, then we turn on failure. As you can see here, it's going to initiate here. It's going to start propagating. Again, it's all autonomous. So we're not really guiding the crack to grow in particular directions or to start at a particular site here. And then, of course, we move on to now periodic modeling of creep, because what happens if you're interested in failure of metals at high temperature? So in this particular case, we considered Blue Murakami creep model, and it has these 3 different phases: primary, secondary, tertiary. And we have a damage evolution guided by this parameter here, omega, and it involves, or it depends on the rupture stress, the multi-axiality. This is the principal stress, the effective stress. So we put everything in here. So that's our basically the creep strain rate. And we looked at this particular 2-dimensional problem. These are the creep law parameters, and we apply stress. Okay, we hold it, and at 240 megapascal, we have the creep strain in terms of number of hours, and we also looked at the damage And for this particular case, they have an analytical solution for one-dimensional analysis, and we compare it against that. As you can see here, they're in very good agreement. Okay, so lastly, we also that now that we have a good handle on non-ordinary state-based paradynamics imposing boundary conditions, so we looked at, okay, what happens if you have beams under finite deformation? So our goal is to look at some architected lattice metamaterials. That's the goal here. And we decided to use Seymour-Reisner hypotheses where you have finite strain. Okay, and that's our kinematics. So these are the unit vectors associated with the plane of the cross-section, and basically this is the vector that defines the centroid of each plane on the cross-section. So we derived our peridynamic equations of motion. We have the resultant moment, then we have the resultant force. And so lambda here, they basically have the moment of inertia and cross-sectional area. So here's an example. So we have a cantilever beam on the moment. So we applied, M1 being 2 pi EI1, and basically 8 times, you can see here, depending on the magnitude of this M1, M2, and M3, is basically you're going to keep rolling it, which is an analytical solution. And it compares rather well. And I'm showing you the animation here. This is like 8 times. Keeps going. This is all finite strain as well. And then we looked at, okay, here we have a slinky under concentrated load. So you have this slinky, you're applying concentrated load here. And as you can see here, we also compared it against finite element analysis, and the comparison is quite well. All right. So now I come back to coupling with FEM. I think I have enough time. So how do I couple the peridynamic equation of motion with FEM? That's the goal. So now I have in the interior, this region here, I have non-ordinary state-based peridynamics, right? Divided by Stilling, 2007. And this one is, we derive this by using peridynamic differential operator in this region here. But this non-ordinary state-based peridynamics doesn't satisfy the equilibrium equation here. But this particular equation satisfies the equilibrium equation. And we enforce the boundary, or along the boundary here, we have the weak form of the peridynamics. So we have these 3 equations that we'll work with, and we'll couple the FEM and PD in a seamless way. And here's an example, okay? So we have a plate, and this is the peridynamic region here. This is the finite element region, clamped, and then we're applying this dynamic load here, and then we, lift it, right, unload it. So we, as I mentioned in the previous slide, I have the region here, which is the region, non-ordinary state-based equilibrium equations derived by Stilling. And this region here is the outer region. The equilibrium equations are derived by a peridynamic differential operator. And this boundary layer region is coming from the weak form of peridynamics. And we are using here traditional elements. There's no overlap region. There's nothing. It's just basically direct coupling. And here I'm showing you the displacement field as time progresses. It's very nice. Then you can say, well, this looks very good, but how about the line plots, okay? And we're also solving this implicitly. That's another challenge. So as you can see here, we're looking at what's happening at this particular point here. This is point, the locations, x equals -1, y equals 1. And that's what we're looking at. So as you can see here, so the FE results and the coupled PD-FE results that I show you, they're on top of each other. And so basically, I'll make a few remarks. What I showed you today is, okay, you have bond-associated deformation gradient tensor. If you use that in constructing the force density vector, then you're going to be free of oscillations. So you're not going to have any zero energy deformation modes. So I showed you the underlying reason for the displacement kinks, because the non-ordinary state-based peridynamics doesn't satisfy the equilibrium equation near the boundaries. So if you use an alternative form based on peridynamic differential operator, then basically you satisfy the equilibrium. You don't need a fictitious region to impose boundary conditions. So I showed you examples of weak form and strong form, and showed you examples also by using these to look at rupture in polymers and basically beam experiencing large deformation, finite strain, viscoelastic material response, and we solved all of these implicitly. So we verified the results against finite element analysis, some of them with experiments, and also I showed you a seamless coupling with FEM and ANSYS framework. I think with this, I will stop. If you have any questions, I'll try to answer. Thank you so much.
Yeah, thank you, Lakmans, for your nice presentation. If there's any question, maybe you can use the raise command. Okay, I have a few questions, Dr. Mansi, about the interface of lap joint problem. Maybe did you have any interface condition for a single lap joint problem?
In this case, we use basically a standard approach that we have. So you can have either like a sigmoid type of a variation as you go. Let me go to this previous slide here. As you go from here to here, you're going to have a jump, right? Some sort of discontinuity. You can basically have either we looked at two different ways of doing it, right? Basically, you can do averaging, or you can basically say, okay, I'm going to approach, for example, Young's modulus as I go from here to here in the form of a sigmoid, right? So it's like a continuous function or hyperbolic tangent, for example. That we looked at both of those. So when you go from modulus going from here to here, you approximate that variation through a tangent hyperbolic function. So
okay. Yeah, I got it.
Either way, you can use it. Doesn't make much difference.
I got it. I have another question, like about coupling of FE region and peridynamic region. So, I mean, how do you couple? I mean, do you have any interface condition? I mean, it's seamless, but in the case of the interface region, I mean, how do you manage this? How do you handle this interface?
Yeah, so basically, we have each of the. So here we're using matrix 27 elements. So it's an ANSYS element, matrix 27. So they share a node. So this traditional element, let's say plane 182, right, is going to have a node here and a node here. But also I have matrix 27 elements. They share the same node. So there is no overlap.
Yeah. Okay. Yeah. ANSYS already has the tool to couple it.